All right, to kick us off with a trio of online talks to finish everything out, we have Christopher Pryor, who's going to talk about ARTop, well, we'll learn soon enough, a program to calculate novel topology-based predictive metrics of active region magnetic field structure. So, Chris, we can see your screen. Can you say something? Make sure we hear you.
Yeah. Can you hear me?
We can indeed. Okay, I'll give you a shout at 5 minutes.
Can you see my hand as well?
Yes, we can.
Cool. Great. Thank you. So, yeah, I just want to thank the organisers for this conference. I don't actually do machine learning. I want to sort of get into using it on my data set, but it's been fascinating to see sort of how much progress has been made using all these techniques. And I'm going to try, as I say, to offer you a data set and try and convince you to help me use it better. So we're interested in solar active regions. I think a lot's been said about this already, and we're interested in flaring. And what I would like is for the use of the vector magnetograms to be better than it currently, I believe, is as standard. So I've got 2 example magnetograms here of regions, which I'll come back to during this talk. But of course, there are always 2 other field components, and there are in the sharp files that people often use some quantities calculated from that, but they're not the kind of stuff we use in the sort of active region modeling community. So I want to be able to give you the stuff we use. And to be clear, the sort of aim is to come up with distributions based on these magnetograms that sort of replace this BZ magnetogram with something that folds in all 3 components. So the basic idea is, we know in these regions, current, flaring, CMEs, they all occur when we have lots of complexity in the magnetic field lines. And we can sort of measure the amount of complexity of these field lines being chucked into the atmosphere. And you can kind of get it in 2 ways. One is if we have a field line embedded and there's some sort of velocity at the photosphere, it can kind of coil the field line up. And we can track that by watching how the points of the field line move at the photosphere. And the other one is a sort of emergence component where some complex fields moves vertically up through the photosphere, and where it sort of pierces the photosphere, these red and green dots, we see this sort of rotation due to the complexity of the structure. So we can get an idea of how much complexity is being shoved into the domain. And this is sort of well established, but our code does actually do the calculations for you. You can track the motion of field points, making some assumptions such as an ideal evolution of the field. Basically, if you can take the magnetic field components, all 3 of them, and then use a velocity inversion to get a velocity field, then we can get this vector field U, which is sort of depicted here, which is the motion of the intersection of a field line at the photospheric plane. So we can kind of track how they're moving around. So given we can track this motion, how do we characterize the sort of this complexity, this rotation? Well, the simple answer is really that we just track the angles made by pairs of points in the domain. So you sort of see it here on the left. As these 2 points rotate around each other, the angle they subtend kind of changes. So we sort of track that, and we're getting an idea of how much these points are rotating around each other. But of course, we're talking about a vector field, and actually there are lots of field lines. And so if we have a sort of grid of points in our photospheric data, I'm going to imagine I'm going to watch how much all of the other field lines are rotating around this one point at the center. So let's say I've got this center point, and these black arrows are all pointing to all the other nodes in the grid. Now, there should be a black arrow pointing to every point in the grid, but just for visual sake, I've just plotted a few of them. And then if we let the field sort of evolve, we see all these points rotate around this central point. And what we're going to do is we're going to measure the average rotation around that central point of the rest of the field. And it's not just the central point. You can do this for any point. I could have taken, say, a point in the top right, drawn all the arrows joining that point to all the other points, and watched how they rotated around it. So for every point in my distribution, I'm going to measure the average rotation of the rest of the field around that point. Okay? So hopefully that's sort of intuitive. wouldn't worry too much about the formula. Essentially, all I'm saying is we're going to call this the winding rate, dLdt. The L means linking, so it's how much they're linking around each other. And if I've got the velocity field and the magnetic field, I can calculate this quantity I talked about. And we've developed a code to actually do this calculation. Okay, so it's quite expensive, but we've got lots of tricks to speed it up. So if we sort of summarize that first section, I've taken the sort of magnetogram data, but also the vector components, and I've sort of folded them all together. And what we've got here are two distributions corresponding to the same time snapshots as above, which show the average winding around each point in the domain from the field. So when it's blue, it's sort of left-handed winding. It's a signed quantity. When it's red, it's right-handed winding. And so we basically transformed one data series by bringing the three components together to another data series, which can be then sort of treated with all the usual methods you guys have been using for feature recognition or whatever you want. And so I guess it's now my job to try and convince you that this is a physically meaningful data set. So I'm going to sort of start arguing by proxy to another quantity. If I take this winding distribution, so this average rotation, but I multiply it by the vertical component of the field, or the magnetic flux, I get a quantity, very well-known quantity, called the magnetic helicity. And this is hugely important in most astrophysical plasmas, actually, but certainly in solar physics, because it's a preserved quantity on average. So its conservation basically drives how the field can evolve. But also, crucially, in this context, it means what we measure of this quantity going through the photosphere is what, on average, should be there in the active region itself. So it is representative of what forms above it. Second thing is this bounds the free magnetic energy from below. So if we've got a lot of this helicity, then we should have a lot of free energy in our system, and then we should expect some flaring if it gets destabilized. And if we're looking at sort of full theoretical models, flux emergence models, and all the like, this is the quantity people have tended to sort of end up using to make predictions. In fact, the first talk of today mentioned this quantity. So this helicity is a very important quantity, and actually what I've shown in my previous sort of theoretical studies is the winding carries all these properties as well. But there is one reason why it's worth also calculating, and why it's slightly distinct from helicity. So, and this actually goes back to a point Manolis raised previously. Basically, if I take on the left here, I have a magnetogram. It's a nice bipole magnetogram. And in the middle, I've got the helicity flux, basically calculating that formula 3. And most of it is basically where the BZ component of the field is. Not surprisingly, because it's weighted by the BZ component of the field. So it's at the magnetic foot points. The winding distribution, this pure angle that I talked about, is always ends up being in between the foot points. So it basically then ends up being over the polarity inversion line, which, as Manolis said, is sort of where filaments form. It's where all the interesting reconnection and all the action sort of happens. So the winding is actually sort of tending to focus on this very important bit of the magnetic field more than the helicity is. And because they look at very different regions, they do tend to give differing information. So we actually calculate both. I'm going to be quite brief on this slide because to actually fully explain it would need a whole talk in of itself. But essentially what it's showing is, what we've seen in simulation, is that the winding, better than any other quantity we've seen, represents the emergent complexity or topology of the magnetic field. The two figures here, the fact that they look quite similar, this sort of rise and plateau, is indicating that the theoretical efficacy of the winding is actually can be realized in observational data, because the one on the right is calculated from observational data, the one on the left is a flux emergence simulation. And we showed this basically could could show that basically that a lot of the complexity of active regions were actually formed below the photosphere rather than due to motions above it in the early phase. But really all I want you to take from that is we can realize this utility of this quantity in real data. So I'm going to sort of round off by showing you how we've tried to start using it for flare predictions, this winding distribution, this data set, if you like. So one of the things we do is we split the observational magnetic field into a potential part, which you can calculate from the magnetogram, and a current carrying part. And of course, the current carrying part is the thing that should actually be causing all the flaring, should be causing the reconnection. It should be the interesting thing.
You have 5 minutes left.
So we can then calculate the winding distributions for, as I described before, but for these two separate field components. And we then take the absolute difference between them. And what you're getting here is a quantity which, if it's positive, there's an imbalance towards an input of current carrying complexity over potential complexity. If it's negative, you're actually getting more potential complexity being pushed in. And so when this quantity is positive, we should expect a bigger likelihood of flaring. Okay, so it's a sort of sensible thing to calculate. I'm first of all going to show you the simplest metric you could get from this distribution at all, which is just integrate it out over each time snapshot spatially, and then integrate also over time so that you get the net input of the imbalance towards current carrying complexity of the field. So that's what's shown in these plots. So we're looking at AR11158, which we've seen a few times already today. This small delta L, little delta L, which is the orange curve, is the quantity I want you to look at. We've got time on the lower axis, and we've got this delta L value on the vertical axis. The gray region is the time period when flaring was occurring, and these yellow and purple vertical lines are actually the M and X class flares for this region. And the first thing is you see this very sharp rise about 20 hours before the commencement of flaring. And this does not occur in non-flaring regions. It does occur in heavily flaring regions. This is not the only example we have of this. And the size of this input correlates very well with the maximum flare type, right? So this seems to be a very good predictor of, okay, a load of current carrying topologies being shoved in, we should expect flaring. And then in this turquoise sort of plot, I'm looking at basically the time derivative of this orange curve. And it's quite a bit messy. The red curve is its average, and this dashed blue line is 3 standard deviations. It's over 30 time series before. And basically what you want to see is there are some points where the input suddenly spikes well above its 3 standard deviations, and it's occurring quite often about 5 or 6 hours before flares. This region, by the way, is when the data gets very dodgy. It's when we're at the limb, so you've got to be careful. But we've got a number of examples where we're sort of almost able to predict these flares sort of 5 hours before they happen. But it's not completely consistent. But just to say, it seems to have some efficacy. This is in a second region, 12673, which had an X10 flare. You see the same rise. And what I want to just very briefly point out is there's this massive jump in this winding quantity just before this big X-class flare. And very briefly, this is the spatial distribution of the winding. You want to look at this one I'm outlining here. At the time of that spike, and you see almost all of the input is in this small region here. And it corresponds here to a negative, blue little velocity, basically saying some magnetic field structure is going down below the photosphere. And if I zoom in on this blue region, and then I zoom in on the vertical component of the field, basically, it's showing me that this was a polarity inversion line. So it was a little highly twisted bit of flux rope, if you like, being pushed down, which led to this spike, which precursored this massive flare. And in full simulations of this, people actually found a flux rope above the exact same region. So it has some physical efficacy. So just to round off, I hope I've got you interested at least in the idea of looking at some of these distributions. The good news is we've got openly available code at this GitHub link to calculate it. It's in C++ and Python. All you need to supply to use it is the sharp number and the time period you want to look at. It then does all the downloading, velocity field calculations, winding calculations for you. We've used SunPy data frame sort of formats for you able to access the data. So it can be used in the same way as you use magnetograms. And there's hopefully going to be a paper released soon explaining this, but I'm happy to send you a version of it if you want to get an idea of how it works. Yeah, and just finally, I have about 60 or 7 regions worth of data if someone just wants to be given the data. And also there's an upcoming 3-year postdoc, which I'm about to advertise soon, on using these data sets to actually generate a proper flare prediction algorithm. So if anyone has interest in this, please look out. Thank you.
Brilliant, thank you. Have we any questions here in the room? Oh, sorry, yes. I'm blind.
Thank you, Chris. This is Manolis, very interesting. It was also intriguing to see the winding results around polarity inversion lines. The time scales might be important here. You mentioned that you seem to have a sharp increase about 20 hours before the flare. I would probably compare this with the flux in the active region, because at least in 1158, this is the time in which you have intense flux emergence. So this flux emergence is obviously non-potential, right? And this is probably why you see the signal. And then the other comment I would like to make is that I don't know if you have come across a very recent publication by Yang Liu and company in the Astrophysical Journal, in which we see a very intriguing, one of the most intriguing event I have seen. If you take a bunch of flares, some eruptive and some confined, then you see that in the area of the polarity inversion line for the eruptive flares, if you get a flux-weighted alpha value, alpha being the force-free parameter, then you see it decreasing consistently. We have used the superposed epoch analysis in this respect. We see it decreasing consistently like 7 or 8 hours before the flare, and then just after the flare, the eruptive flare, it peaks sharply in a stepwise fashion. And we don't see anything like that in the confined flares. So just magnetic reconnection events. I was wondering whether your results could be combined with these, because there might be a lot of physics in both of these two results, particularly if combined.
Yeah, definitely, absolutely. I think that the thing is, what we can offer with this data set is something with a lot of topologies either being shoved in or pulled out of the domain. So there's a big event, but it can't tell you really physically, or just as it's used here, it can't tell you physically what that was. So I think the idea is to sort of cross-correlate this with both extrapolations. I was very happy to see actually this morning, one of the speakers has actually released their code to do that, which is very useful. So I can actually grab some of these extrapolations, but also check it against a lot of these sort of flux tubed identification metrics, because it would be nice to understand what these events were, because, you know, this particular one I highlighted is very small. It's like it's almost like it might be the bottom end of a flux rope being pushed down or something. So it would be nice to try and find out what they are, what these events are, I guess.
Yeah. Thank you.
Never.
Have we any other questions in the room? It doesn't look like it, and nothing online. So I guess I'll thanks again, Chris, for a very interesting talk. Yep.